Hey ladies and gents, welcome to probability. Let's take a look at where this is at in our course. So here's the diagram of our course, all the different topics, and we're done now with this stuff down here, which is descriptive stats, units G and C, and of course the intro. And what we're moving into right now then is a completely different branch of mathematics, probability, so unit P, and then those two will go together to bring us into probability distributions and then eventually into inferential statistics. So that's where we're at here. And let's then head back then to our page here and talk about probability. This is not a long unit, so it'll just be a couple, 3 lessons maybe. Here are the topics on probability here. So down at the bottom here it talks about that we will be defining probability, talk about the probability model, types of events, and independence. One thing to note about probability is that you have been dealing with probability statements all your life. So for instance, a question right now is, what's the likelihood that you're going to catch COVID-19? And so you probably have some idea as to what that is, and you've probably adjusted your lifestyle to that. You may have some elderly parents or grandparents, and so you might adjust your lifestyle in terms of whether you're going to spend more time with them or less time with them in order that they not catch this, right? So I read actually an interesting article just today that's talking about what are some of the factors that go into why certain types of people in certain nations and so on tend to have higher COVID rates. And so they were saying that if you speak Spanish, actually, that your chances go way up in terms of contracting COVID. Now, they're actually talking about it on a national scale. So they're saying that the nations where Spanish actually is the main language tend to have a higher rate of COVID. And so that's kind of interesting. And does that necessarily mean that one causes the other? And the answer is no. And so it doesn't necessarily mean causation. And we'll be talking about that when we get into looking at regression at the very end of this course, and also when we go into the next course, which is Business 307. It's also interesting to say that there are a couple of nations which have populist governments, and they are very high up, so they're specifically talking about the US and Germany. Now, does that become a factor which increases the chance that you're going to catch COVID or not? And again, that doesn't necessarily mean so. However, more importantly, I guess, is that what they're finding now is that younger people are catching COVID more often, and that's because they're going out and doing things. They're not locking themselves away, and so there's a lot more interaction, a lot more exposure to it. Anyways, if I was to ask you what is the probability that you would catch COVID, say, in the next year, then you might give me a number like, well, it's maybe 5% or 10% or 50-50 or something like that. And what we'll see is that you actually have a pretty good idea in terms of how we talk probability and statements about that. So let's jump into taking a look at some definitions, first of all, and then we'll take a look at various rules around probability. And the thing to note here is that a lot of this stuff you're going to look at and say, I saw this back in junior high even, probably, and certainly in high school. And so you'll find by the end of the unit that we're getting into some stuff where you're going to have to scratch your heads a little bit more in terms of how you solve these things. So let's take a look on page P2 here, the definitions of probability, and we're going to make a distinction between a subjective probability and an objective probability. So a subjective probability is an estimate by a decision maker as to how likely it is that an event will occur or has occurred based on subjective estimates, prior knowledge, and experience. Now, this doesn't necessarily mean that this is an uninformed guess. So you've seen the stats for COVID and so on, and so you probably have a reasonable idea in terms of what your probability is of catching this disease in the next year. It's probably somewhere between 0 and 100%, but it's what might that mean for you? And so you're going to take a look at a number of different factors on that. If you're a sports fan, I might ask you, well, what's the probability that the next time that the NHL plays, that say the Oilers are going to win the cup? And usually I can tell if I ask my class that all the Calgary fans say 0. All the Oilers fans give a high percentage, and so on. And of course, as the year progresses, if this were a normal hockey season right now, then we would already see some games that are being played, and so we would get an idea. And so your projection or your estimate is subjective, but it's still based on knowledge. And as we get closer and closer to the finals, then of course you'll get a more accurate guess as to what that is. I might also ask you then, what's the probability that it's going to snow tomorrow? And so you might look outside and say, well, I think it's something like 50-50 or something. And then when you pull up the weather app, then you're going to get a much better idea in terms of that. Now, is that a subjective probability or is that an objective probability? An objective probability is the limit of the relative frequency with which an event occurs on the long run. So there's a guy named Carrick who tossed a coin 10,000 times, and he recorded the number of heads and the number of tails that he got there. And so I thought I think I was watching a Disney princess film with my girls many years ago, and so I was doing the daddy thing, but they were getting into some princess stuff and so on like this, and as I was watching this, my mind started to drift, and I thought, I think this might be a good time to try the Carrick experiment. So I pulled out a coin, and I flipped the coin. And I didn't do it 10,000 times. I just did it 50 times, but I did make a recording here of what I got on each toss. So in the first case, what I got here was on toss number 1, I got a tail, and that means that now we can count either heads or tails, it doesn't really matter, but I'm taking a look at heads. So at this point then, I've got 0 heads out of 1 toss, so that's a relative frequency. Remember, that's your frequency divided by n, which would be the number of tosses here, is equal to 0. And then the next one I got a tail again, and so I'm still at 0. And then the next one I got a head, so I'm at 1 in 3, which is 0.33. Then I got a tail, and so that's now 1 in 4, so that's 0.25, and you can see what happens when we go down here. If you take a look at the diagram on the next page here, the chart on the next page, what it shows here is the relative frequency of heads by the number of tosses. So as I got closer and closer to 50, what I want you to note here is that I got closer and closer to 0.5, which is what we would expect for a fair coin, that 50% of the tosses would end up in heads and 50% would end up in tails. It's very erratic, obviously, at the very beginning. You can see that, but it does tend to even out. And that's what Carrick found, was that when he did it for 10,000 times, that he might have even got 20 tails in a row, which isn't likely, but it doesn't make much of a dent in the relative frequency, the long-term relative frequency, when you're talking about 10,000 times. So what this says here then, going back to the definition of an objective probability, is the limit. That is, if we were to do this theoretically an infinite number of times, then what is the probability that you would end up with a head? Well, if it's a completely fair coin, it would end up being 0.5. What's important to note here is that if I were to ask you, what is the probability that you get a head when you toss a coin, you'd probably say 50-50. And then if I asked you why, a lot of people will say because there's two sides. That's not the answer. That's really important to note. Okay? It is the answer because coins are made so that they're fair. That is, that there's an equal probability of getting a head or an equal probability of getting a tail. By the way, you might hear some furniture moving upstairs. That's what all the growling and stuff is up there. Let me give you another example of that, and that is that what is the probability that you will, well, let's say die of COVID-19? And you could say, well, you either die or you don't die, so there's two possibilities, so it's 50-50, but we know that's not true. It's actually much, much smaller than that. It's more around 5%, or depending on whether you have some other conditions or not, it might be higher. Okay, so let's continue on here and talk about the probability model. Some definitions here. An experiment is any situation capable of replication under essentially stable conditions. So that would include things like tossing a coin, obviously, and rolling a dice, rolling a die. Let's just say rolling dice. Drawing cards. But then what about things like the weather? And you might look at that and say, well, it's not essentially stable conditions here. But what we have found in terms of the weather here is that we're actually pretty good at considering the weather to be an experiment, in that we're getting better and better and better actually in terms of predicting what the weather is going to be. And although we tend to remember the times when the weather report is wrong, it's actually fairly accurate. And so when it says that there's a 90% chance of rain, usually it rains. And if it doesn't rain, people say, well, the weather was wrong. The weather report was wrong. No, because they didn't say there was a 100% chance of rain. And it doesn't even necessarily mean in your particular spot. It could be in the whole area, the whole district, whatever your particular forecast covers. And so we would tend to say that because weather and the conditions for weather are pretty much replicable, that we can come up with some pretty good estimates of that. We know that it's going to snow sometime in the next while. And in fact, there's snow on the ground right now. So as soon as you hit October, there's a good chance that you're going to end up with permanent snow, certainly into November, and by December almost a certainty, right? And in January, I've never known a January where there wasn't snow on the ground. And so you can say that that is an experiment, whether it's going to snow this winter or whether it'll snow tomorrow. What isn't an experiment is something like World War II, because that's not replicable, right? What a student gets in this class is, because although I don't experiment on you folks, I can come up with a fairly good idea as to how you're going to do on particular exams as a class here, because I know the averages of the exams, and when I do some tweaking or changing, the likelihood that the marks are going to go up or down. An outcome is an indivisible result of an experiment. So if we're talking about the experiment of tossing a coin, then it's a head or a tail. And we wouldn't include things like landing on the edge or something up against the wall. We would consider, a flat surface where it does end up with either a head or a tail. But what's important is that we'll see an example in a bit here where we defined an outcome as tossing 3 coins together and recording what we get. So the indivisible outcome is what you get on one toss of 3 coins. So we'll see that in a few moments here. An event is a collection of one or more outcomes. So that might mean something like, what's the probability of getting at least 2 heads when we toss 3 coins? The sample space is the set of all possible outcomes. When we take a look at the 3-coin example, it'll make more sense when we look at that. And then I want to make a distinction between a discrete and a continuous sample space. So a discrete sample space is one where the outcomes are counted. So we count the number of heads that we get in certain tosses, or whether it rains or not, number of males in a group, etc. A continuous sample space is where the outcomes are measured. So the time to the next thunderstorm and things like that. Length, weight, mass. Even when you're talking about mass, even though you do tend to round things to the nearest pound or kilogram or gram or milligram, depending on what it is that you're measuring here, or ton. Although we tend to round it to that, we can actually go into smaller and smaller and smaller units here. So we consider it to be continuous. Another thing which I think I've mentioned in a past video here is with discrete things, you count them. So you say the number of people. You never say the amount of people that were at that particular event. That's actually a bit of a bugbear for me. And so you only talk about the amount of people if you're putting them on a big weigh scale and weighing them, or you're measuring the volume of people. But you actually count people. So you say the number of people, not the amount of people that were there. And that's a very common mistake that people make. Some probability axioms. An axiom is like a hard, fast rule. It's definitional. It's never broken. So, first axiom is the probability that an event A will occur is expressed as a value between 0 and 1, or if you like, between 0 and 100%. So, when I asked you what you think is the probability that you'll get COVID-19 in the next year, you probably came up with a number like 5% or 50% or something. So it's probably expressed as a percentage or as a decimal value or as a ratio. But it's always between 0 and 1. 0 means it's impossible and it'll never happen. And 1 means that it's a certainty. It will happen, or it has happened in the past. If there's something in the past and you don't know what the results are yet. Number 2, in an experiment, some outcome must occur. So when you flip a coin, if the experiment is, what do you get when you flip a coin, then you get either a head or a tail. And there's no other possibilities. So again, we are not including the possibilities of it landing against the wall and it being on its edge. That means the experiment wasn't done properly. Number 3 is a really important one, and I want you to star that one, is the outcomes in a sample space must be mutually exclusive and collectively exhaustive. Mutually exclusive means that if you get a particular outcome, it means you didn't get the others. If the simple experiment is flipping a coin, if I got a head, it means I didn't get a tail. They're mutually exclusive. If I roll a die, and the experiment is how many spots turn up on a single roll of a die, then if I got a 1, it means I didn't get a 2, 3, 4, 5, or 6. Collectively exhaustive means that if you make a listing of all the possible outcomes, then they exhaust all possibilities. There is no more. So in tossing a coin, the only 2 outcomes are heads or tails, and there's nothing else. Together, they exhaust all possible outcomes. Rolling a single die, there's 6 outcomes, right? Probability formula is number of outcomes comprising the event over the total number of equally likely outcomes in the sample space. So we'll be seeing how we use that later. All right, let's take a look at an experiment here. And so the experiment, actually, it says define the experiment. Actually, that is the experiment. It's kind of a trick question there. So the experiment is that a penny, if you can find one these days, a nickel and a dime are tossed together, and the face, whether it's a head or a tail of each outcome, is recorded. So that's the experiment. List all of the outcomes for the sample space. So what I'd like you to do here is, let's put down a penny, a nickel, and a dime, and then I'd like you to list down here the outcomes for that. So this would be a good place then to stop the video. This is what I would be doing in a class, is stopping and then asking you to take a moment out here and to list them. So do that now, stop the video, and make a listing. Okay, I'm going to assume that you've done that, and there are 8 possible outcomes. So you can get 3 heads, or you can get 1 tail, and that tail could be in any of 3 positions, or you can get 2 tails, oops, that's a head, or you can get 3 tails. So 1, 2, 3, 4, 5, 6, 7, 8 outcomes, and that is what we call our sample space. Now, let's take a look at axiom number 3, because it says down here, show that the axiom number 3 holds. So axiom 3 says that the outcomes of the sample space must be mutually exclusive. Mutually exclusive means that in my experiment, if I toss 3 coins, then one of these outcomes will occur, and if I got, say, 3 heads, it means I didn't get any of the other outcomes. So as soon as you get one of the outcomes, it excludes the other ones. Collectively exhaustive says all 8 of these exhaust all possibilities of outcomes. All right. Okay, let's take a look here then at some probabilities. What's the probability of getting exactly 3 heads? So that would be like that. And let's change colors here. I'm going to use different colors for each one of these. So that would be this guy right here. That's the only one that has 3 heads, and so that is 1 outcome out of 8 possible outcomes, 1/8. Second one here is, what is the probability of getting at least 1 tail? So at least 1 tail, or 1 T. So take a look here and see what you get here. So at least 1 tail would be anything that has a tail in it. So it could be 1 tail, 2 tails, or 3 tails, and so it excludes the first one, where you had 3 heads, pardon me. And so the answer here is 7/8. What is the probability that you get 4 tails? And that's equal to 0, because none of the outcomes has that. There's only 3 coins, right? So that's impossible. What's the probability that no more than 1 head turns up? Let's change colors again here. No more than 1 head. So if we take a look at that, we'll see that doesn't include 3 heads, and it doesn't include 2 heads. So it would include these guys here. So 1 head or 0 heads. No more than 1 means 1 or 0. And so that's going to be 4 out of 8. And then the last one here is, what is the probability that exactly 1 or 2 heads will turn up? So let's change colors here. So 1 head or 2 heads. And if we take a look here, we'll see that that is these guys right here. So it excludes 3 heads and no heads. And so that is 6/8. By the way, a question that you might ask here is, do we have to reduce the fractions here? So, for instance, 4/8 up here then is equal to 1/2, and 6/8 is equal to 3/4. And the answer is no, you don't need to do that. I assume that you can do that. You learnt that many years ago, and so you can just leave it actually in its form 4/8 or 6/8. All right. I think we're going to stop this video at this point, and then we will pick this up next day.